Unit 2, always start off, hopefully early on in these newer chapters or beginning chapters, you'll have some vocab, so you can always reference that. Today we're actually going to start off with atomic theory, and we'll be talking a lot of theory today, so pay attention. Hopefully some of this you may have accidentally learned in junior high or in some other science class, and again I say accidentally because we do learn as we go along, hopefully. Some early atomic theory, and again we're talking way back in the day before I was born, which was so long ago. We'll talk about this guy. But atoms are so small that they cannot be observed directly. We still do not have the technology to look at an atom and go, ooh yeah, there it is. Okay. We can look at molecules, large molecules, but we don't have the technology to look at an atom directly. We can smash the atoms and see the particles fly off, but they leave patterns and trails. But we can't actually look at it and say, yeah, that's what that looks like. So we can't associate it. So we have a pretty good theory. There's a lot of evidence to help support what we believe and what we say the model looks like. So it's not still like, you got to have faith. Faith is for religion. Science, we have facts. But they are very small, and we have a lot of experimental data to help us determine what the shape of the atom looks like or how it's arranged. Around 400 BC, I'm not going to try to pronounce that guy's name, a Greek philosopher suggested that the world was made up of two things, empty space and tiny particles. He got his name in the chemistry history book for that. You got nothing and tiny particles. Brilliant. All right, during the 1800s, so a big jump, almost over 2,000 years here, French chemists discovered that chemical changes occurred in a closed system. The mass of the chemical changes equaled that from which we started. In other words, he came along and said, you know what, if I take, say, 4 grams of carbon and 4 grams of oxygen, put it in a reaction chamber where none of that's allowed to escape, I better get 8 grams of material back. And he got put in the history book for saying that. In other words, what that's leading off of is that matter's not created or destroyed. Okay. Hopefully you've heard that before. And there it is, the law of conservation of mass. So that's a pretty big concept in chemistry. We don't create anything. We don't destroy anything. Even in nuclear reactions, we're not making or breaking, we're not making or destroying anything. We're just rearranging. And that's what this whole topic's about, is just rearranging things. Law of definite proportions. Some of you like to breathe out carbon dioxide. It's one of my favorite waste products. However, if my furnace is not acting correctly, it'll produce carbon monoxide, which behaves a lot differently than carbon dioxide. I don't want to be around carbon monoxide as much as I want to be around carbon dioxide. Now again, if it's just carbon dioxide, it's probably a bad thing. But law of definite proportions states that no matter if I'm here in Avon or in Brownsburg, if I run across the carbon dioxide molecule, it's going to have 1 carbon and 2 oxygens. Same thing if I go to Jupiter and find a carbon dioxide. The law of definite proportions state that that's the way it is. Now that sounds kind of stupid. The first time I heard that I thought, really? This is what they're telling us? Yeah. So law of definite proportions tells us that there is a given ratio for our things that we're working. And the first one we want to talk about is Dalton's atomic theory. And Dalton came out with some proposals about chemistry, and again, it was in its infancy. And chemistry is relatively a young science. It's just a little over 200 years old, 250, 260, so it's still a puppy, so to speak. Elements are made up of tiny particles called atoms. Groundbreaking. Okay? All atoms of a given element are identical. In other words, all atoms in a given element are alike in mass and other properties. So it doesn't matter where you're at in the universe. If you're looking at a carbon atom, it's going to be the same here as some other galaxy or wherever. The atoms of a given element are different from those of any other element. That's really important. That's actually a big statement. Atoms of one element can be combined with atoms of other elements to form compounds. A given compound always has the same relative numbers and types of atoms. Okay, we'll talk more about that when we put these guys together. And atoms are indivisible in chemical processes. What does indivisible mean? We say it every morning. Never ending.
That's infinite. Sorry.
So it means we're not going to be able to break them apart. Okay, so when they're indivisible, you can't split them up. And the key is under chemical processes. Now, he didn't know about the nuclear reactions, which is good. I'm glad they didn't have that technology back then, or we probably wouldn't be here. In other words, they can't be created or destroyed. In chemical reactions, and again, that deals with chemical reactions. We'll talk about nuclear a little bit later on. A chemical reaction simply changes the way the atoms are grouped. And we'll talk more about the arrangement of the electrons more than anything else that takes place. And according to Dalton's law of multiple proportions, again, what that means is just because I have a carbon and an oxygen doesn't mean it will always form carbon dioxide. Multiple proportions means that carbon, for one thing, can make 100,000 more, actually more than that, compounds. So there are different combinations that these atoms can do. All right, it's not just, if I've got a carbon, I've got an oxygen, it has to make carbon dioxide. Not true. Okay. So there's where our multiple proportions, but definite composition. Hopefully everybody knows this. The subatomic particles that make up an atom: proton, neutron, and electron. Who's in the nucleus? Or what makes up the nucleus, I should ask.
Nucleolus.
You're thinking cells. These are your three options. What makes up the nucleus?
Protons. Protons and neutrons.
Protons and neutrons. So these guys, atomic number. When you hear me say atomic number, I want you to think protons. Okay? And more importantly, protons identifies what you're looking at. So if I'm looking, and you can look at your periodic table, if I'm looking at something that has 7 protons in the nucleus, what element am I looking at? So N, which is, does anybody know what N is? Nitrogen, very good. Now, how did Renee know that? Well, it's the numbers that you look at on the box. And the box, if you're looking at the box, it's the number in the top, what's that, left for you guys? Okay, it's the number that has no decimal, but it's a bigger number. In other words, larger. All right, so atomic number is the number of protons. That identifies the atom. Okay? And again, that's what I have on there. Isotope. Isotope. But an isotope has a set number of protons because that tells us what atom we're looking at. But isotopes have different numbers of neutrons. So they have different masses. So like, for example, we have carbon-12. What that means is the mass is 12, and again, the mass is due to the protons plus the neutrons within the atom.
Isn't that negative 12?
No, that's a dash. Yeah, carbon-12. So since we already have 12 protons, then that means, well, we have 6 neutrons. Now this is assuming that I assume that you guys know something. What's the mass of 1 neutron?
2 electrons.
0.
1 proton.
Yeah, it weighs the same as 1 proton. Okay, it's very, very close. So when I say that we're looking at a mass of 12, then that means that the protons and neutrons have relatively the same mass. Okay, actually it has the majority of the mass. The electrons do have mass, but they're so small that we ignore.
That's under the letter?
Could be, so it's like 12.01. Okay, that number is a little bit different. We'll talk about that one later. But looking at a single atom, it'll always have, if I'm looking at carbon, it'll always have 6 protons. However, if it has a different mass number behind it, that means it has a different number of neutrons. But you got to remember, protons identifies what you're looking at, so that number is always going to be consistent. However, the neutrons can change. That's what an isotope is. All right, unstable isotopes are often referred to as radioactive. So we'll talk about that when we do nuclear stuff. I'm not going to worry about radioactive stuff just yet. The number of protons determines the identity of the element. The number of neutrons determines the isotope. Actually, I was talking about the number on the bottom. That's this, the mass number. Okay? The mass number on your periodic table, which is just below the symbol, and that typically has a decimal place, is the average of all the isotopes that we know of. Okay? So the number that has a decimal is the average of all the isotopes. So like if I had 30% carbon-12 and 70% carbon-14, we would take the average of that, and that would get us our mass number. Now that's not their actual percentages. I would say that the majority of the carbon atoms that exist are very, very close to 12, where there's not as much 14. To find the number of neutrons in an atom, we're going to take the atomic mass, which is the number of the protons and neutrons, and we'll subtract that from the atomic number, which is what again? The atomic number is?
Number of neutrons.
Protons, very good. So that'll give us the number of neutrons that we're looking for. So the mass minus the number gives us the neutrons. Okay. And we'll do some of those here shortly. If an atom is neutral, protons have what charge again? Positive. Neutrons have what charge? Neutral, none. Good. So electrons have to have a negative charge. Good. So electrons are negative, protons are positive. So if I have an atom with a neutral charge, and I say if I'm looking at carbon again that has 6 protons, it has a +6 charge. If it has 6 electrons with it, which it should when it's neutral, then that's -6 + 6 makes it 0, or neutral. Okay? So when you're looking at neutral atoms, they have the same number of electrons as protons for your given element. And that's what this says. The atoms are ordered on the periodic table based on the increasing atomic number. Back in the day, it went by mass, which really screwed things up. Okay, so we arrange it by atomic number. And again, the average of all the isotopes together. And we'll have some exceptions where you'll see, for the most part, the masses increase as we increase the atomic number, but there are a few exceptions. I think that's one of your homework problems. All right, the correct way to write the symbol, this is not how it appears on your periodic table, which stinks because some of you are like, oh man, that number on top is flipped, okay? And this is for a single atom. This here is for a single atom, okay? Not for what's on the periodic table. So when we do these type of things, and we will here in a moment, the mass number is always on top. And again, the mass number, if you want to write this somewhere, is protons plus neutrons. So draw an arrow to 39 and say, mass number, protons plus neutrons. The atomic number equals protons. Now, the other thing that's not listed on here is in this top right-hand corner, is the charge. If there's nothing there, what can we say about the charge of this atom? It's neutral. Good. So if there's nothing there, it's safe to say that it's neutral. If we put a +1 there, then it has a +1 charge. We'll talk about what that is here in a moment. If it has a -1 charge, then it has a negative charge. Okay. All right, let's do looking at your periodic table. So looking at your periodic table, I think on the notes it had the example of potassium, and you'll get a sheet so you can learn these names and symbols because you'll have a quiz over this.
No.
I think on Thursday. I think I changed it. Yeah. No, not all of them. Not all of them. All right. So looking. Okay, we had 39 and 19. Okay. So I may ask you. All right. The P with the plus charge, that represents your proton. The N with no charge, that represents your neutrons. And the E that looks like that represents your electrons. I'm going to go ahead and put a charge on here. Okay? All right. Protons, how many do we have? Protons. 19. Because again, this number right here is your atomic number, or the number of protons. Okay? How many neutrons do we have? 20, good. So we take this number minus that number. So this number minus that number. That's why I like this number on top. I didn't get to pick that. That's the way the chemistry geeks before me chose. So 39 minus 19 gives me a 20. Now here's the big question. How many electrons do we have if potassium has a +1 charge? If it were neutral, we would have 19. But it has a +1 charge, so
18.
why 18?
Because you subtracted negative.
Very nice.
What?
So in that case, we have to have 19 plus charges, and then if we add that to 18 negative charges, that'll give us a +1 charge.
What?
I know, right? So we have to have 18 of those. All right, remember protons have a plus charge, electrons have a negative charge. If the total charge on my atom is +1, that means I have more protons than I do electrons. How many more? I have one more than the electrons. Okay, now here's another thing that you have to remember. Electrons come and go, no big deal. Protons stay put. So if I have a K up here, I better have a 19 there. If I have, say, a C, I better have what number there? A 6, okay? So on and so forth. Yes?
So if it was like a +2 charge, then would you have 16 electrons?
Okay, the question is, if this is a +2 charge, how many electrons should I have?
There's 17.
There you go, I like 17 better.
Sorry.
Okay. Now, potassium won't have a +2 charge, but if it did, and we can live in our fantasy world here for a moment, if it did have a +2, then yes, it would have 17. Now let's go even further and stretch our imagination. Okay? Potassium will never have a -1 charge in here, but if it did, how many electrons would it have? 20, very good. And remember, it's the electrons that can change. Protons are locked in for an element. So in this case here, we have one more electron than we do protons. Yeah, Ashley.
So if that's like a positive at the top corner.
Are we talking here?
No. There.
Here?
Yes, there.
Okay.
If it's like plus something, then you subtract it from the atomic number.
I like
and
that.
If it's minus, you add it.
Yeah, that's what I used to term Avon math. In other words, to get this value here, if this was a +1, I need to subtract to get the right number if it's positive. Okay. Let's do an I and 28 down there. And let's go with 60 on top. Now let's say it's +3. Okay? Does anybody know what Ni represents? Don't say nitrogen.
Nickel.
Nickel, very good. Okay, that'll be one of your 52 as well. So protons, neutrons, and electrons. Okay? How many protons? 28, very good. So that's our proton number. How many neutrons? 32. So this minus this. And electrons? 25. Excellent. Okay. All right, here's another way that I could attack you. Okay, you're given this information. Now you tell me how to write the symbol with all the fun information on there. Okay, so first of all, what symbol are we looking at?
Read the numbers first, and then figure out what you're looking at.
Yeah. Yeah. What is V? Vanadium. It'll be one of your 52. Is it V?
Yeah.
Vanadium? Okay, so we'll go with V. My pen is done. There we go. All right, so we got our symbol. You got to have the correct symbol, or else everything's a train wreck.
I like it.
One side.
What goes here? 23. Very good. That's how we were able to determine that it was V or vanadium, based on that number right there. Okay. What number goes up here? Good. Now, here's one thing I want you to notice. If you look at the periodic table, it says 50.94. Okay. You will never have one of those numbers up here because this represents a single atom. One atom. One atom of vanadium. And again, these represent all the atoms of vanadium that we know about. All right, what goes up here? Plus what? Plus 4? Excellent. Everybody like that?
Yeah.
Throw another curveball. Okay? Here you're given another set. So what letter am I looking at? I. Does anybody know what I is?
Is it I?
It is. Just getting them. I like that. All right, so what goes down here?
53.
53, very good. What goes up here?
123.
So you add, wait, you add the neutrons and protons together.
Yes, to get the mass. Yeah, so we'll add these two to get this top one. Excellent.
No, wait, negative charge.
Protons are always on the bottom.
That would be negative 1.
Not electrons, but the charge. Okay. So what goes here?
Negative 1.
Negative 1? Yeah?
16.
16?
Oh. What is that? Who said 16?
It's all right. All right, everybody good with this? You'll have some homework dealing with that. And if you watch this on the video, there's a bright spot here. That's why I'm trying to get it as low as possible. When you are asked to find the average atomic mass, or what the scientists did to get these values here, this is what they did. They went out, they scoured the universe, Earth, okay, and they found their material and the mass amounts, okay, and then they found their percentages. So hopefully these all add up to 100. I think I did check it a couple times that does equal 100. And based on these values here, because we'll always have a whole number because you have protons and neutrons within your nucleus, then it depends on what the percentage is and how much we have. Now, if we had, what do we have, 5 here? Yeah. If I were going to add all these up and divide it by 5, which I wouldn't even think about doing in this case, why? Well, it'd be wrong, but why would I not just add these 5 up and divide it by 5 to get the average?
They're separate things.
What's that mean? Yeah, they're separate. I agree.
Like they're not for the same atom.
Oh, it's for the same atom. They're all different isotopes for that atom. What is so important that we wouldn't just add these 5 up and divide it by 5 to get the average?
Because no one element can have the same mass.
They could, but these guys right here, this is your hint. What are these not all? The same. These would all have to be 20%. Whenever you go and average something, it's assuming you have equal percents or equal amounts of those things. So like when you go and figure out your grades, like I think in here, your tests are worth 50%. So your tests would be worth 50%. Your quizzes are worth 25%, your homework and your labs are worth 10%, your finals worth 15%. So you don't just take all the points and then divide it by 4 in that case, but we have different percentages. So here's what I do. I have my mass amounts given here, and then I have my percentages with the decimal place. I simply move the decimal place over 2 places. Okay? Now in some cases, it'd be nice if I had a marker that could write. In some cases, like with this point 07, or I'm sorry, this 7 point whatever, I have to actually put a 0 in there, a placeholder. Because if I just put the decimal in front of the 7, now it makes it 77%. So move the decimal over 2 places for each one. Okay, so now I have these, which are my decimal equivalent to that. Take these numbers, multiply them together, and get 0.1. Now, if you're good and you can put all of that in your calculator, that's great. When I have these values, I simply add them up. Once I have that number, what do?
Divide by 5.
Don't divide by anything. Walk away and go to the next problem. That's what moving the decimal over 2 places does for you. It takes away that dividing step. Okay? If you did not move the decimals, you could still do it that way. But then you'd add up your numbers and then divide by 100. But here you don't have to. All right, so let me add all these. So what'd you get?
50.33.
Okay, 50.33. And that's what my calculator's saying. So I got 50.33. Now, as a real quick check, and you should do this every single time, what should my average be between? In other words, my answer, this is my average, should be between 45 and 55. That's a real quick check. If I got a number that's not between 45 and 55, trust me, you don't have the average. So 50.33, yeah. And again, this is the majority of it is 52, so we would expect it somewhere in this range. However, if you had an answer of, say, like 5.0 033, check your math. You did something goofy there. Or if you had something like 503.3, check your math. But your average should be between your lowest value and your highest number, okay? So that type of mistake you don't ever want to make on a test or a quiz. Okay? So again, whatever your percentages are, if I gave it to you in decimal, go ahead and move it over 2 places to the left. That way you just take this times this, get your number, add them all up, bam. Okay? And that's how we got all the values on the periodic table. I personally didn't do it. So let's start talking about Dalton's model of the atom. Dalton proposed that his atom, and again, this is early on in the game, so we didn't know, we didn't have the technology, we didn't have the wherewithal to know any better, but Dalton's model of the atom was one of these. Okay? It was a solid sphere or ball that had an even consistency throughout. He didn't know anything about protons, neutrons, or electrons. He just said, this is the atom. It's a ball. And the world's made up, or the universe is made up of these things and empty space. And there was this cathode ray tube. Thank God we are getting away from cathode ray tube televisions, all right, or the monitors. I love these flat screens. I love my HD. But back in the day, the reason why, does anybody still have a cathode ray TV or a big fat TV? There's got to be a few out there. Okay. So you get the special converter box or a dish or something hooked up to it, and it's this big. Okay. However, now the cathode ray tubes work on the principle of electrons. All right. So we have one end of the tube that is the cathode, the other end is the anode, and we'll talk a lot more about cathodes and anodes when we get into AP Chem. But we just want to talk right now that the cathode end is where the electrons originate, and then the anode is where they go to. Now, in this diagram here, let me find this diagram first. This diagram here is how our cathode ray TV works at home, if you still have one, or your computer monitor, if you still got the big monitor. We originate the electrons here, and they move in a straight path, just like light does, moves in a straight path. However, as the experiments were going on, Thomson accidentally, and I again say accidentally because he didn't do this on purpose, he accidentally had a magnet nearby and noticed that this light was being scattered. Well, guys, if you've ever played with a flashlight and a magnet, has anybody ever tried this? Take a magnet and your flashlight and bring it close together. What happens?
I have no clue.
Nothing. Absolutely nothing. The light keeps going forward, okay? Trust me, I've tried it. However, with these things, with the magnet, we'll say that this is the positive end of the magnet. The electrons actually went toward the magnet. Light doesn't do that. The only time that it can do that is when it gets around a large gravitational body, or a big body that has a nice gravitational pull to it. So the beam of light was bent, and Thomson goes, whoa, that shouldn't happen. And then he took the the magnet, and put another one there, and had the light go down and then up. Dang, he said. Okay, so we were able to direct it, or he was able to direct this pattern, or this path of light, by having some magnetic influence. And based on the magnets, he figured out that the light went toward the positive end, and what did it do toward the negative end? It wanted to get away, because again, positive with positive is a bad deal. Negative with negative is a bad deal. But positive with negative rocks on. Okay? So Thomson worked with that a little bit more and said, you know what? The atoms have to be made up or have these electrons within them. So Thomson came up with a new model and actually found out the electrons and said, you know what? Atoms have electrons. So Dalton's model was now changed to a ball with some negative charge associated with it. Okay. Protons. When Thomson was looking at this, and here's a picture of the cathode tube right here, and it does emit that green light, he noticed that the electrons were the dominant force or dominant pattern moving from left to right, but he also noticed a lesser pattern moving in the opposite direction. So if the negative charges go this way, from left to right, and the positives go right to left, then that means that there's a positive charge there. So he formulated and came up with protons. Okay. So now this atom has protons and electrons. He just doesn't know where they're at yet. Okay. And what he did for this was he came up with a new model. He formulated or changed Dalton's model into what they call, I guess it was the big dish of the day. It was called the plum pudding pie model.
Wow.
Plum pudding. Plums and pudding in a pie model. And what that is that you have your sphere still, but the protons and, I'm sorry, the positive charges and negative charges, because they didn't have names for them yet, were just scattered throughout like raisins in a raisin cookie or something. Okay. All right, so I like that. It does sound interesting. Tomorrow we're going to talk more about how this model has evolved into what we believe today. So go ahead and work on the ones and the twos. The naming elements worksheet, front and back, this is for you to complete on your own. I'm not going to check it. However, we will have a quiz.
Thursday?
I want to say Thursday, but let me look.
I already marked it in orange highlighter.
In orange?
Yeah, for caution.
Let me look. I don't want to lie to you guys.
How are we supposed to know what they are though? Because they have weird things.
I know, right?
Should I Google it?
Yeah, there you go. There's Thursday. So Thursday, a B day, and we do meet. So during our review day, we'll start off with that. Now, here's what I would suggest. Go ahead and fill this out. And it's going to take more than 5 minutes. Go ahead and fill this out. Front and back. Because on one side is the symbols, on the other side is the names. And you're going to love me for this. They're not in the same order on both sides.
Oh, yay!
And I would make flashcards. Now, some of you don't believe in flashcards, but they'll help. I would put on one side C, just the letter C. On the opposite side, I would write carbon, not calcium. If I wanted to have calcium on the back of my card, I'd have what letters in front? Yeah. Nice. Okay. Now, here's a fun one that you have to know. I probably should stop recording at this point. If you look at the side that has the symbols, I want you all to find this. SB. Where are you at, SB? Where's SB at? Number 15 it looks like, on the side that has the symbols. Anybody know what SB is?
Subrillium.
Close. Antimony. Okay. Yeah, antimony. SB. Now remember this. Now hold. You'll never forget it after this moment. Okay. SB is antimony. Okay. Now here's how you remember that. Listen. I don't want you to forget. And again, I shouldn't be recording. But SB is antimony. Antimony rhymes with alimony. And if you have to pay alimony, you have to pay that son of a...
Wait, can you repeat her again?
I don't think
It's on the tape.
Wait, do it again. Say it again.
Wait, how do you spell
No,
that?
I was gonna do something.
HSB is alimony.
No, it's not alimony. I did not say it's alimony. It's antimony. Antimony rhymes with alimony. And if you have to pay alimony, you have to pay that son of a... Does anybody know what, let's look at another one here. And this one is from one of my former students. Number 31 on the same side, PB. Anybody know what PB is? Lead. Very good. So don't put peanut butter in your lead. Or don't put lead in your peanut butter. Okay. So go ahead and make those up Thursday. When we walk in the door, you'll get that quiz.
Oh, dear.